2022 AP Calculus AB free response question number 3. We have a graph of a derivative of f, so let f be a differentiable function with f of 4 equaling 3, so they give us some initial condition that's likely going to be of some use in this problem. On the interval from 0 to 7, 0 to 7 both inclusive, so we have a closed interval we're working with. The graph of f prime, the derivative of f, consists of a semicircle and 2 line segments as shown in the figure above. At this point, you can pause the video and look over parts A through D and see if you can answer these on your own. And what we'll do is progress through each part and we can see how we did. Now this is a non-calculator question, our first free response question that is a non-calculator question on this 2022 exam. So let's take a look at part A. So we need to find the output value of the function f at 2 distinct points. Now, in this case, we're working with the graph of f prime. And when we're trying to figure out something about f and given f prime, your first inclination may be some sort of integral is going to be involved. Now, we could try to come up with an equation that defines f prime because we know that it's composed of a semicircle and just 2 line segments. So it would be possible just to write a little piecewise function here for f prime. And then we could determine, okay, f of x is going to be that integral, that indefinite integral of f prime of x dx. And then we're going to have some constant of integration that we're going to get at the end there that we'll be able to determine through that initial condition, and then we can evaluate the function thereafter. But the antiderivative of f prime after composing that piecewise function may be difficult to compute. So instead, we're going to use some geometry in this case to determine what the value of our outputs are going to be at these specific points for the function f. Now, if you recall from our fundamental theorem, when we integrate along an interval from a to b of some function, that's going to equal its antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So if our function that we're integrating, in this case f prime, the antiderivative being f, we can see that when we take the antiderivative of f prime, we're going to get a difference in the outputs at 2 points. And isn't it convenient that we already have the output at 1 point? So that second point we're going to use are the points that we're after. So let's use that fundamental theorem to determine f of 0 and f of 5. So now that we've discussed that the integral is going to give us a difference in outputs, we're going to say f of 0 should equal some initial condition value plus that difference in outputs from where we started to where we want to end up, which in this case is at 0. So we're going to integrate from our starting point to where we want to go of our function that is available, which is f prime. Now, f of 4 is given, so we know that's 3. Now, how do we integrate from 4 to 0 for f prime? Again, we do not have to write an equation given this graph. We can just compute area under the curve. Now, in some cases, you may want to flip this integral, and whenever you change the lower and upper bound or you swap them, make sure you change the sign of the integral to minus. But just a reminder of what this integral is doing. This f prime and this dx you can think of as the base and a height for a rectangle, right? We're computing a Riemann sum as the base of those rectangles approaches 0. So this represents our height, this represents our base. So if we're integrating from 4 to 0, the base value would be negative. We can see the function output on that interval on this graph is going to be negative, which is why when we compute this area, the result is going to be positive. You would have learned that the integration along a closed interval when given a graph is the net or the signed area under that curve, right? So if we just understand how the integral works, where we have a base and a height, the dx part in this case would be negative. The change in x going from a higher value to a lower value on our graph, that dx in this case is going to be negative when we're working this way, which is why traditionally most will put the lower value as the lower limit. So again, totally acceptable to do, but if we can just recognize how this thing works, we don't necessarily have to do that. So we know that although this area is below the x-axis, it's going to be positive because we're working from right to left here. Now, what is the area of that semicircle? Well, the area of a circle is pi r squared. We can see that it's centered at 2, so we have a radius equal to 2. But in this case, we want half of it, so when we square that radius, we'll get 4/2, so we're going to get 2 pi. And that is the value of f of 0. And we would have got that same thing if instead of at this point we did 3 minus, we switch and we go from 0 to 4, f prime of x dx. And now because we're working from left to right, our base of our rectangles in the Riemann sum are now positive. The function output is still negative in that section of the graph. So now we're going to get negative 2 pi as the area under the curve, and we still get that plus 2 pi. So we have just found what f of 0 is. So now let's move on to what f of 5 is, and we're going to do that same process just with a different ending value. So we're going to say f of 5, this desired function output should be equal to an initial condition that's given to us plus the change in the function outputs from where we started to where we want to go. And how do we do that? Well, we integrate, because that fundamental theorem tells us that integrating a definite integral is the result of the antiderivative at the lower or the upper bound minus the antiderivative at the lower bound, indicating a difference in the function outputs. So we're going to work from 4 to 5 in this case. F prime of x dx. We know what f of 4 is given. It's 3. Now we're integrating from left to right. And in this case, that section of the graph that we're going to be looking at from 4 to 5, we're going to have a triangle area to compute. It's above the x-axis, so it's going to be positive, right? Our base of our triangles, or rectangles, sorry, that would be used to calculate that area in the Riemann sum is positive. The function output is positive. So our integral sign is going to be positive when calculating this area under the curve. So how do we do this? We're going to need to know what this point is, so we know what the height of our triangle is. We know that that point is at 5, 1, and we know that because the slope of this line is 1. We can see it has a rise of 2 and a run of 2, indicating a positive slope of 1. So I know that point's 5, 1, and therefore the height of that triangle is 1. The base also being 1. So 1/2 base times height, we're going to get 1/2. So f of 5 is, we can add these together, and we'll get 7/2. So for part A, we found both f of 0 and f of 5 using a fundamental theorem of calculus and recognizing that evaluating the definite integral when given a graph is just finding the area between the x-axis and the curve itself, considering the sign, very important. So we use an initial condition and we add to it a way to compute the difference between the output values of where you started and where you want to end up. That between where you started and where you end up difference is what the fundamental theorem of calculus tells us we're computing upon a definite integral. So just quick review before we move on. When we integrate this function, we know that it should be antiderivative at the top minus antiderivative of the lower bound. And as we can see, this is a difference in function outputs. So that was part A. So what's the scoring breakdown there? We're going to get 1 point for f of 0, 1 point for f of 5, and we're also going to get 1 point for this area calculation, recognizing that that's what we have to do for each one. Moving on to part B, find the x-coordinates of all points of inflection for the graph of f from 0 to 7. So when I want to find the points of inflection for the graph of f, we're going to need to observe f double prime, which is going to be the derivative of f prime. We have the graph of f prime. So we'll know that we have a point of inflection when f double prime changes signs. So when is this going to happen? F double prime will change signs when the rate of change, F prime of F, changes from increasing to decreasing or decreasing to increasing, because F double prime is a measure of the rate of change for the original function F. So we just have to look at this graph of F prime and determine where does this change from decreasing to increasing or increasing to decreasing. So we have 2 points in contention here. At x equals 2 and at x equals 6, we can see that the graph goes from increasing to decreasing here. And then we have one that goes from decreasing to increasing here, which would imply that our second derivative, which is a measure of the rate of change of this graph of f prime, is changing signs, right? It would go from negative to positive and then from positive to negative. And whenever we have a change of signs in the second derivative, we have just identified a point of inflection. And that's going to be our justification as well. So we're going to say that we expect point of inflection, so at, or we'll say, how about we say f has a point of inflection at x equals 2 and at x equals 6, because at x equals 2, f double prime changes, or we'll say this, at x equals 2, f prime changes from decreasing to increasing, implying f double prime changes from negative to positive, and at x equals 6, f prime changes from increasing to decreasing, implying f double prime changes from positive to negative. So we have explained that we're recognizing to identify a point of inflection, we need to analyze the second derivative. And to analyze the behavior of the second derivative, we look to this first derivative graph, knowing the second derivative represents the rate of change of this rate of change graph for f. And we identify the 2 points in this case, and then we give it some reasoning. So what's the point breakdown there? We're going to get a point for our answer, so x equals 2, x equals 6, and with that justification. So now let's move on to part C. Let g be the function defined by g of x equals f of x minus x. On what intervals, if any, is g decreasing from 0 to 7? Show the analysis that leads to your answer. We will know if g is decreasing if g prime is less than 0. So we have to find g prime. Now, f is differentiable, so we'll be able to represent it with a derivative, and we can differentiate x. So we'll say g prime of x is equal to f prime of x minus 1. Now, we need to know, well, when is g prime of x less than 0? That will determine when it's decreasing. So when we look at our graph, g of x, we have now noticed, is this equation here. And when I'm given f prime, how do I interpret what's going on in this red box? Well, minus 1 we know is a translation down 1 unit. So if I just shift all of these points down 1 unit, so we'll just highlight the major points. We'll have to add a negative 3 in here. What I'm drawing in red, we now know is our graph of g prime. And we want to know, when is this thing less than 0? Well, now what I'll highlight in blue is the portion of the graph that's less than 0. So we're going to say from 0 to 5. We're not going to include 5 because it equals 0 there. So we're going to say, so from 0 is less than x is less than 5. Because g prime of x is less than 0. So what's the point breakdown here? We're going to get a point for calculating the derivative of g prime. Then we're also going to get a point for the interval given where it would be decreasing, and then a reason as well with that. So that's all there is to part C. We used our knowledge of translations and how to compute a derivative and how to analyze it to determine where a function is decreasing to answer that question. So now let's move on to the final part, part D. For the function g defined in part C, find the absolute minimum value on the interval from 0 to 7 and justify your answer. We know to find an absolute minimum, we're going to be analyzing that derivative of g once again, and we're looking for a transition from negative to positive signs for that derivative, implying we would have a minimum point. So we're going to have to check some critical points. But also, because we're working on a closed interval, we'll want to check these endpoints as well to make sure that those are in contention for our minimums potentially. So now let's rewrite our derivative of g. So we determined in the last part that g prime of x is f prime of x minus 1. We want to find its critical points. Now, because f is differentiable, it was continuous, and therefore g must also be continuous because g is defined as f of x minus x. So maybe we should write that somewhere because we're going to have to evaluate g as well. So let's write that up here. G of x is f of x minus x, and we know that g prime of x is f prime of x minus 1. So g is continuous, therefore differentiable, because f was differentiable, we know that, and continuous, and the function x is also a continuous thing. So when we come to find critical points, we don't have to worry about undefined values there. So all we're looking for is when is g prime of x equal to 0? So we're going to redraw that g prime again, just quickly. We understand that it's a shift down 1 unit. And we're going to see that the critical points have now been identified at x equals 5 and x equals 7. So when we make our little sign chart for g prime, we're going to consider our endpoints 0 and 7 because it's a closed interval. And then we're also going to throw a 5 on there, another critical point. Now, what about the signs? Well, from 0 to 5, g prime is negative and then positive. So what does this mean for each of our critical points, including the endpoints? Well, from 0, that means it's decreasing. So this is going to be a max. Because it goes from decreasing to increasing, that means 5 would be a min, and then 7, it's increasing to 7. So g would have a max at 7. So the only thing we're concerned with is x equals 5, which means that must also double as our absolute minimum. If we had more minimum values to consider, then we're going to have to evaluate the outputs at each one and make a comparison to determine which one is the absolute minimum. But we know 5 must be the absolute minimum, but we also have to find out what that value is. So it's not just good enough to say where it happens, but what exactly is it? So we know that at x equals 5, g has an absolute minimum value of, now what is it? Well, we have to find what is g of 5. Well, g of 5 is f of 5 minus 5, right? So we're using this g of x function. We're going to evaluate it. Now, what's the nice part about this? We already found f of 5 in part A, which turned out to be 7/2 minus 5. So g of 5 is equal to 7/2 minus 10/2. So g of 5 is equal to negative 3/2. So we have an absolute minimum value of negative 3/2. And the justification for that is because g prime of x changes from negative to positive, implying a minimum at x equals 5 for g. it was also the only minimum point on the interval 0 is less than or equal to x is less than or equal to 7. So it must also double as an absolute minimum on that interval. And what's the point breakdown for part D? Well, we're going to get a point for recognizing we need to find critical points. So somewhere saying g prime of x is equal to 0. And then we're also going to get a point for our answer, which was that -3/2, and with the justification. So we're justifying it by saying we recognize that g prime changed from negative to positive, implying a min. And then how are we recognizing it as absolute? Well, in this case, it was the only minimum in contention for that title on the closed interval from 0 to 7. And that is all of question number 3 on the 2022 AP Calculus AB exam.